Okay, we're going to look at an argument now for electrical potential energy that is fairly similar to the argument that we went through when we looked at gravitational potential energy. The only difference here being that if we have a positive charge here and a positive charge here, then the force is a repulsive force, whereas in the gravitational situation, we were dealing with an attractive force. All right, so we're talking about moving a charge from particular position, R, out to infinity. Now the force would be given by if you force against position there. We're looking at the area under that graph again for an inverse square law force. And so we are, effectively we have to go through a whole process of differentiation, but I'm not going to go through that process. Now the work done in moving the charge from position R to infinity, because naturally the charge is going to be repelled, and we're looking at the work that not this charge is doing, but the work that we would be doing on charge Q and take it to infinity. In actual fact, that charge would be doing work on me if I was trying to sort of hold on to it as it was heading out towards infinity. So therefore, the work done in this particular case, and hence the change in potential energy, and therefore ultimately we'd get through to the formula for potential energy, it's going to be a negative amount of work done. And so using a similar sort of argument that could have been gone through for the gravitational fields, we get Q over 4 pi epsilon 0 R. And it's got a negative sign in front of it there because of the fact that we're going from R to infinity. Don't get too hung up at the stage about the negative sign. Let's move on and follow this through just a little bit more. If capital Q is negative, then what we'd have is we'd have our negative charge here, we'd have our positive charge here, and there would be naturally a force of attraction that way. So we would have to actually do work on the charge to move it out from R to infinity. So the work done, and hence the EP in this case, would be a positive value, Q over 4 pi epsilon 0 R. Okay, so that would be taking it out to infinity. We want to take these ideas now and use them in terms of potential, okay, which is where we're heading. So let's just remind ourselves about electrical potential. In year 12, we basically had this formula V equals W over Q, work done per unit charge. But we're going to refine that definition now to say that the electrical potential at a point is the work done in bringing unit charge, just take note, from infinity to that point, from infinity to that point. So if we just flick back to these previous slides, this slide over here, the work done in moving the charge to infinity is going to be negative. The work done in bringing the charge from infinity back to that point would be a positive value, okay? If you start off out here at infinity, if that's where infinity is, and let's on this diagram here, and we're bringing the charge back in, then we would be doing a positive amount of work because we're having to move this charge, little q, against a repulsive force. So then it would be a positive value. Similarly, for this situation here, if we've got a positive charge that's naturally attracted, then the amount of work that we would have to do on that charge to bring it from infinity back this way would then become a negative amount of work. Okay, so let's take that idea and work through things from there. Okay, let's just find my notes for this section. All right, so if we've got EP being Q over 4 pi epsilon 0 R, And we've got this formula V for potential being work done, which is effectively equal to change in EP, work done over charge. We better make that little q because it's the work done on the charge little q that we're talking about. Then we end up with the formula Q over 4 pi epsilon 0 r divided by little q. The little q's cancel out. And we end up with the formula being Q over 4 pi epsilon 0 r. All right, now, if this charge capital Q here is positive, then that implies V is positive. If this charge capital Q is negative, then that implies V is negative. All right, so you've got a symmetrical situation here where, let's just flip over to the next page to just illustrate that. Let's ignore this example just for a minute. If we've got a charge Q, then, if it's a positive charge, say somewhere in here it might be 150 volts, somewhere here it might be 30 volts, and ultimately as we head out to infinity, we head towards 0 volts. If it was a negative charge, then that might be negative 150 volts, negative 30 volts, and as we head out to infinity, 0 volts again. Okay, so we've got negative potentials when we've got a force of attraction between this negative charge and a positive test charge. So force of attraction, just like with gravitation, we end up with negative potentials. But if we've got a positive charge there, then we've got a force of repulsion, and so we end up with a positive potential instead. Okay, you don't need to write this stuff down, it's just really by way of explanation. Okay, let's get rid of that, and there's a worked example for you to go through. All right, we want to find the potential. Okay, so what you do, one thing we should have noted, and we didn't really note, we should have done, is that potential is a scalar this time. We said that electric field strength was a vector, potential is a scalar, and so you can add things together, but you just have to take into account positive and negative signs. So what we would do here, we've got this plus 5 microcoulomb charge, so let's work out V due to that. So V is going to be Q, because it's a positive charge, it's a positive potential, over 4 pi epsilon 0 r. Let's go there, probably if we can fit it in. So 5 by 10 to the negative 6 over 4 pi times 8.85 by 10 to the negative 12 times 0.06. So you work out that one, and that's going to be a positive so many volts. And then do the same sort of thing for the negative 10 microcoulomb. V equals, you can do that, and you're going to get a negative value there. So you're going to get a positive value there, a negative value there. I think because we're closer to the positive charge than we are to the negative. Trouble is there's different size charges, so I was going to say that one's bigger than the other. I can't really predict that so simply. But let's just make up some numbers. Let's say that worked out to be 1.5 volts and that worked out to be negative 0.7 volts. Then the potential at point P would be 0.8 volts. All right, so you just add the two potentials together. All right, potential gradient from the AS course. We know that E is equal to V divided by X. All right, so let's say we've got an electric field like so, which is just sort of varying. It's not a straight line now. If we want to get the electric field strength here, it's the rate of change of electric potential with distance. And so a more general form of the formula is to say that E is equal to dV dx, or you could say delta V over delta x if it was a linear sort of a field. And the other thing that we do is we throw a negative sign in the front. That's covered down the bottom here. This term dv dx, or delta v over delta x, let's write that down as the other possibility, delta v over delta x, is known as the potential gradient, all right? The rate of change of potential with distance. The negative sign used because when there's an increase in potential, if we're heading this way, opposite to the direction of the field line, that would correspond to an increase in potential. And so the fact that the increase in potential is the opposite direction to electric field strength means put a negative sign to indicate that.